Okay, that's not very beautiful, but whatever. Okay, once more. Okay, so always think in the 2 dimensions, right? And you can see that there's various forces in place, but they always in the end are vectors. So that means the resultant always can be split into the parts in order to make the resultant. So if you see the F force, for example, that's clearly, I mean, like this, right? So there's some force going up, right?
Yeah.
Otherwise it wouldn't. So on the other hand, like what you said, S is now in that direction. So let's go back. So actually you have one you indicated already, but clearly that's not helping at all because it has to offset the one from this one, right? And there you see the balancing act on this part. And on the other hand, of course, you have to think about, well, F is going up. Do you have any, let me see, did you have to calculate any F? We'll talk a moment about P, on the road at P. And so the wire, there's actually, well, when you really, the weight. Okay, we are leaving R aside, right? Because the fixation of the wire is actually an issue as well. Otherwise, you can't hold it in place. But we neglect that here. That's why I have to check. It's because it's just really a simplification, right? You have to think about the force at P, but of course, you have to think basically at R as well. But we only focus on the rod. So that's why it's not quite complete in the considerations. And so what you say, so is it clear now that S has to have a second direction as well?
Yeah. Yeah.
So for the Y part, is that okay for you now or understood? They just say Y S is going in that direction instead of just in the red, so it needs to have that component as well. Huh?
But well, if like so for F, the force of the like the tension, why isn't the upward force there enough?
Okay. When you think of it, if you think about, you know what, I'm switching to the there I can a bit easier make it in the. So let's go here. And let's do it like that. Okay. So you have the wall. They have 2 points. You have the rod. Thicker. Yeah, well, that's not the idea. That doesn't matter. So you have a rod here, huh? Now, if you would have the rod on, and we have, let me see what they say. This is only the weight of the rod, right? Yep. Okay. Of course, it has a moment as well, so we have to consider that one too. But simply speaking, so, and we have the weight of the rod, huh? So let's put it like that. If you would have no wire, then how would it look like? So imagine no wire, huh? So no wire here. So what do you have to think about when you have to say, well, how solid basically has to be the fixation of the rod, right? Because it's only hold here, so you probably have to have the rod some part into the wall. the material has to have a certain density or whatever, so it can exercise a force on holding the rod. What do you have to consider first of all? I mean, it's in the question as well. When you just have no wire and you have the weight of the rod as indicated, what will generate that weight?
There will be a moment.
Yeah, exactly right. So we have a moment like this as a result. So what do you have to therefore create in order to hold it in place?
The same magnitude of the moment to the opposite direction.
Yeah, exactly. Very good. Huh? So we do the anti-clockwise. So if that's the moment, sorry, that should have been red. Then of course we have the moment the other way around, right? So is that the end of it? Or would you have to think of moment is one thing? Would you have to think of forces as well? Because we have identified a moment, right? That's fine.
Yeah.
But what about W?
Well, we need equal amount of force upward.
Yeah, right, exactly. Huh? So let's do that. It's something here inside, right? So an anti W, so to speak, huh? Or W stroke. Because you could obviously there's no force pulling the rod out, right? It's not. It's just you don't even have to fixate it, so to speak, here, so it's not slipping out because there's at least in theory in our model no force to pull it out. So as long as there's no force pulling it out, we don't need anything in the other direction to keep it in place. That could be glue or some cement or whatsoever, right? Or a physical thing like what we call an anchor, which has maybe some ripstops which then go in, and that inside is the rod. And so these ripstops go into the cement, so to speak, in order to, by contact force, holding it in place. But there's no such thing, so we don't have to worry about that. However, here, and of course, that W stroke is exercised or created by the wall, right? I mean, it has a force here. And actually, the one on top, of course, we need. Otherwise, if we don't have the wall on top, so to speak, then it will just be whoosh. The moment will just twist it up. And that counter moment here will be created by the wall on top of the rod. And the wall underneath the rod, so to speak, is creating the counter weight to keep the W in place. Otherwise, it just drops down. Yes, it will be perfect against the moment upwards. So that one weight tries to make it like clockwise turn, but because of the wall here, it will be prevented. But of course, it could just go down because nothing holds it in place. So it's always important. It's very obvious, but when we think of forces, nothing is obvious. But we just have to say, you know what, if I draw the whole thing, the free force diagram or the free body diagram, then of course I just have to say, well, there's a moment here, there's a moment there, there's a force, sorry, the other way around, there's a force here, and there's a force there. Everything's balanced. No? So this one is balanced with the red one, and the red one is the origin of the moment, and we need then a counter force, orange, to make it like that. So if you look at it like that, and if you leave that aside here, then of course something is missing, right? Then clearly it will just go down because there's nothing holding it here actually. And that's exactly what it plays with now. So from that angle, we need a force in this direction. Now to make it more complicated, we have that wire, right? And that creates additional forces. So of course, that's what I was thinking. We don't talk about it here because these forces are needed as well. Otherwise, it won't help, right? But we just think about that force F, which is clearly along the line or the wire. That makes, of course, perfect sense. How otherwise can the force travel, if you want to say so, or transmitted, kind of? And of course, but in reality, as we always say, we have to think in XY. basically we have the two vector components in the anti-direction and in the upward direction, right? And the beauty of that is that the reason why, or let me ask you, why does it make sense to introduce a wire here instead of the situation before without wire? What's the advantage to have a wire?
It takes less force to cancel out.
What was that point R, I think, huh? I think we call that, yeah, P, sorry, and the other one is R, okay. So this one we call R, and this one we call P, exactly. So otherwise the full force, like we had it here, without wire, it's the full force, right? W, and here it's W in the other direction. The moment we introduce the wire, of course, sorry, that's not quite correct. So I should put it into halfway. So like that. And of course, if we have the wire going up like this, so of course the wire, let me see, maybe let's take purple. So of course we know, obviously, we have something like this and something like that. Otherwise, we don't have F here, right? At the moment we draw that, we realize, okay, just by sheer mathematics or physics, you can look at it in both ways. By saying, well, I have always a y-x direction. And as I already put my force into the two-dimensional rule, right? I do not just have it along x or just along y. That would be like each one direction. No, I have it put into the plane, so to speak, which is made up by x and y. So it's a two-dimensional arrow, of course, which is made up by the one-dimensional arrows of x and y. So the moment I do that, because I have to think like this, I cannot think in this F direction, so to speak. Well, I can somehow, but typically we don't. We rather split it into the Y and the X. So that means, well, if there's one like this and one like that, so this one now takes all the weight from this one, but that's not possible because we know we need to have a fixation here, which we have identified without the wire. But of course, what will happen with that W stroke? Like you mentioned in verbally, what will happen to this force in terms of magnitude by having introduced the wire?
It uses less.
Exactly. We can fairly assume if that's halfway through, probably we probably just half it, right? So basically we have the Fx here, which is W half, and we have the W stroke, which has become now in the new situation of the wire, has become, of course, half of what it used to be before. Exactly. So that's the reason that it gives additional force support, which seems from the outside very obvious. Well, okay, I only have the rod here. That seems a bit unstable. Well, in reality, actually, the rod can be very stable if it's properly fixated here with the right dimensioning. So I have all the counter force here. That's okay. And that's all I need, right? And it has to be strong enough, of course, for the momentum for the moment as well. That's an obvious part in any case. But of course, by having the force here, it helps to reduce the moment because it goes somewhere up here as well, right? This one all the way here creates a moment, and that will, of course, give some counterweight to this one because it will be turning around that angle actually. So it has that distance and that force. Hence, we have a moment here in the other way direction as well. And of course, the green one, sorry, that went a bit too fast. The green one, of course, goes counter. Counterclockwise. Huh? This one will create another counterclockwise force. So same thing, right? We have the situation that we counter, the moment will become less, and that is usually, that's called torsion sometimes. Later on, you may use that word. It's kind of a torsion, which will be exercised onto the fixation here. And that is usually not so easy to hold in place. But if we now reduce the torsion by half here, because we have introduced the wire here, which creates its own moment with this distance. So of course, we have less on this side actually, because it goes in the same direction as this one, counterbalancing the one which creates this one. So long story cut short, in the end, when we look at it, we have to say, well, obviously, like indicated, I need the force going up, and henceforth, that's this one. So, and of course, it counterbalances the one from the F, from the Y. Henceforth, that's the resulting one I see, the S. Huh? Is that okay, Chris?
Yeah. Yeah.
Okay. So it's always these three body diagrams. They are well liked, actually, and they're always a good answer to any of the questions if you just de-link it from what is actually being talked about: a wire, a rod, a crane, a flag, a weight, so whatever. You just say, well, okay, whatever. I just make my free body diagram, and then I start to put it into the XY direction, and that's when I start to see how I can solve the question. And then it becomes standard, independent, flagpole, crane, or whatever else the question is all about. Huh? Okay, so I would like to do more momentum today, if that's okay. There's a lot of questions. We will see there's two levels, medium and hard. So we do a couple, let's see time-wise. Maybe to start with one hard question to be a bit, to see a bit how the hard questions go. But we start with this one, huh? Very typical. So we want to determine the velocity of x before the collision. So what factor do we take into consideration?
Because ball X stops when after it collides, that means all the momentum is transferred.
Okay. All right. So how should I write that down in the proper equation? It's correct what you say. So let me just write it down what you said. That's good. So the momentum of X has been transferred to Y because of the situation description. X stops, Y starts moving. Y was not moving before. Okay. So now what are the equations? Sorry.
V is 140. V equals 620 times 0.8.
Okay. Okay. So you see, always write it down completely, Chris, because I mean the zeros are it's important message, and it will, if in doubt, you will always get some marks for that. And I would suggest as well I mean, it depends, but then you can give it either an index, like say 1, 1, 1, 1, 2, 2, 2, 2, right? Whereas the mass, of course, is the same, so you can eliminate that again. As the mass stay the same, but the velocity is not. Huh? So that would be the most complete equation before we go into the values, right? That we write it completely down before and after, and the before and after is indicated with the velocities as situation 1 and 2. So it can be as well before B and A or whatever, doesn't matter. And then we can write it down like what you just said, because with this one is 0, hence it's 0, etc. So that's just the extensive version. But in a test, it's usually good to write more the extensive version as well. Okay, now, as we've already written it down, so what do we get? Like you said, we have 140 V. What is 0.8 times 620? Or we can leave it. 620 times 0.8. And the answer, what is V now?
496 divided by 140. 3.5.
Exactly. 3.5, exactly. Meter per second. Very standard. Okay. And very typical situation. And then you look at the velocity. So of course the ball, sometimes of course the ratios are very nice. So for example, if this one would have been 560 as a factor 4, then that would have been expressed itself in the speed, of course, as well. Now, because it's a bit less, it's 4 point, not even 5, 4 point something, 4 maybe. Hensworth, of course, this one is multiplied by 4.4 as well, right? So that's the relationship, because it's a very simple, straightforward, linear relationship. So of course, if especially one is 0 before and the other one is 0 after, then you just have one simple relationship between that one as a product of mass and velocity compared to, of course, mass and velocity. And hence, as they have to be equal, as we of course come to the second question, then we have to say, well, obviously the ratio of the masses expresses itself in the ratio of the velocities. What this one is a fraction of y, hence the velocity afterwards of y must be a multiple of that fraction. Is that clear what I mean, Grace?
Yeah.
Just say, no problem. So that's one of the where you have a linear relationship, so you don't have to nothing square or whatever, which is very typical in physics. Here it's very nice, just mass product, mass and velocity, and they must move in the same way, unless of course there's a split. As long as there's some, for whatever reason, the velocity here. So now, why is that inelastic? Or what would we expect under normal circumstances? Let me ask that first. What is more the kind of standard case usually in our model assumptions? Elastic or inelastic?
I think when it's elastic, then the kinetic energy is conserved.
Yes, very good, exactly. Because even when we say it's inelastic, we still calculate it on both sides, the kinetic energy, right? And then we compare, and if they are not the same, then we say it's inelastic. But nevertheless, we calculate the kinetic energy, exactly. In the assumption of the simplified model we usually approach, and say, well, there's no energy lost, right, in the collision, so to speak. So it just gets transferred 100%. That's why probably here, and with the momentum, that has been conserved. We know that. That doesn't prove it, so we have to go into the kinetic energy, exactly. That's the point. Kinetic energy of before or situation 1 is probably greater than the kinetic energy after. Or of course we could rephrase it the other way around and say, well, the kinetic also it's the same, of course. Kinetic energy afterwards is less than the kinetic energy before. But same thing, but it's a bit a different focus, right? Here we focus on what happened afterwards, and you say, well, after the collision, there's probably less kinetic energy. Otherwise, that's why it's inelastic. So we lose some energy in between, or different type of energy actually. Whereas here we just say, well, what we started with is not what we are ending up with. So it's really a matter of the focus we are given, or we are giving to the question. Now, in order to calculate now, what do we have to calculate now for I or for 1?
140. I mean 1/2 times 140 times. Wait, I mean like 1/2 times 0.14 times.
Yep, that's a good one. Yep. Times
3.5 squared.
Exactly. That's why we needed to calculate, right? Otherwise, sometimes you don't get the question like this. Sometimes it's just all in one. Basically, maybe it's not asking first for the velocity, like here, because it's missing. Maybe it's just going straight to that question.
Oh.
Then you have to identify yourself that, oops, in order to do that, well, I can, of course, show the kinetic energy formula and the relationship, but then I realize what is missing. So then I have to figure out, how do I now calculate the missing velocity, for example. Then obviously you have to think about momentum in that regard. So, but here there is usually still the split step-by-step question. Okay, that's one thing. And what is that? Should that be equal to? Let's assume now we say it's equal to, or we can of course calculate it just separate before and after. Maybe in this case, as they already state it's inelastic, we may not say it's equal to, we just calculate it. So that's before. And what about after?
1/2 times 0.62 times 0.8 squared.
Exactly right. So straightforward. And kinetic energy, always same story, so to speak, but we have to put it into context. And if we calculate it, what do we get for before and what do we get for after? I mean, I can just jump ahead. Okay. Before, it will result in 0.86.
Yeah.
And it's because we all have made the kilograms and everything, so it's joules. And afterwards, we get 0.2. Ooh, that's massive. No? So, Hainsworth, what can we say now, Chris?
It's inelastic.
It's inelastic, exactly, because before is greater than after. Or maybe although that's not really the best way to do it. This one is greater than the other one. Or we just repeat it again, like what we said before. So kinetic energy before is greater than kinetic energy after. Proven and take. We shown that. Because inelastic means this one. All right, good. And how can we explain that? Why is there such a loss? What happened?
I think it's because I don't know why.
Okay, that's fine. You imagine when you have these two balls, so that or one stationary, the one moving. So that ball, of course, would roll here, tendency, but nevertheless hits the ball. Here it's a bit easier. Otherwise, you get a spin even because you would have a moment actually. So it hits it here. Say it's flying, to make it a bit easier. What will they? You probably will hear a sound, right? Most likely when they bang into each other. So sound, of course, is energy as well, right? And it has not been existing before. So that is one way where the energy will be used in order to create the sound energy, sound waves. That needs energy. The other one is that at the contact point, there's probably must be, according to what we've calculated, some heat. So the contact point, there must have been some friction, obviously, between the 2 points at the contact, and that heat, of course, is lost in the transfer, so to speak. Typically, that's if you do not have a permanent deformation, like when we would have a collision of two cars and then it gets clearly stated both cars got some damage, of course, then a lot of the energy went into damaging or changing the structure of the car, because without external force, of course, the car will not change its shape, right? It needs an external force. And that, of course, is not anymore contained in the kinetic energy. Assuming now we look at a situation where both still move to some degree, so not the typical crash and standstill, but crash and still slide a bit, then yes, you still have some kinetic energy because both cars still move even after the crash, at least a few milliseconds maybe. But a majority of the energy has been lost. And that is, of course, going into the deformation energy, as we call it quite often. And as we do not have that in this situation, then the only remaining one is basically heat from the impact, friction of the impact, and some sound as well, to a lesser degree. So you can use that as a standard answer if there's ever coming such a question. Okay.
What if
yeah,
the before and after were switched? Like the ball Y.
You mean the big ball into the small ball?
Yeah.
Mm-hmm. Good question. Given so the ball Y would travel at with the 3.5, right? Or with 0.8?
Like 0.8.
Yeah, because otherwise it's a very different ball game in the truest sense of the word, right? So it would be the same. Well, when you look at it, well, it's a good question. So if you just turn it around and say, well, this time before it's half, times 620 times 0.8 square, and the other one is afterwards 0.140 times 0.35 square, right? Is that any different?
No.
Right, so we calculate here. We calculate 0. and now I see what you mean. So that would okay, yeah.
Oh, wait, it's
0.86, right?
3.5.
Yes, thank you. So what we can say here is that cannot be, right? I mean, it could be. It's a good question, Chris. That you say, well, okay, if it's just the other way around, so we just did that. So the after becomes before and the before comes after, right? So what you can see here is it must be that at least we would have to exchange the velocities. That we say, well, the bigger ball comes in with the higher velocity, the one we calculated before as before. So it still has to be like that, and then go with this one. Because we have because we cannot have, if that's now before and this is after, because we say the bigger ball comes with 0.8. So we just turn it around. That's not possible, right? Because we 0.2 joules is clearly less than 0.86. So it cannot be that energy has, that means energy would have been induced before is less than after. Or in other words, after is greater than before. That's physically impossible. So it's a good question. So you could say, well, if you just turn it around and say, oh, what happens? If we just say, well, this time the big ball comes at that, or what we had as a collision situation afterwards with the big ball at 0.8. So we would have to say, no, it would have to be, let's try it out, that the big ball is traveling at a high velocity. That starts to make sense probably. and the small one has afterwards still a small velocity. What do we get when we calculate that, Chris? Just
there should be decrease in energy.
So how exactly as an expectation, do you have the values?
Wait.
Yep, let's just do it.
3.6.
For the first one,
Yeah.
3.5 squared. I get 3.8. Let me see.
Oh, yeah, 3.8.
Okay, that's fine. Okay, 3.8. And what for the other one? We get 0.8 squared times 0.07. Something like 0.05. Do you get the same, Chris? 0.8 squared.
No, 0.0.
So,
Yeah.
0. Basically 0.5, right? So, which makes and why does that now make a lot of sense? I mean, obviously the loss in energy is tremendous, right? So the delta kinetic energy, the loss is massive. It's basically nearly everything we have in kinetic energy gets annihilated and only a tiny little part. What could be in that case an explanation? I mean, is it of course in reality most likely it will not happen like that. Most likely there will be a much higher velocity for this one.
Yeah.
Most likely. So we would have to recreate a new situation, of course. But assuming now, okay, whatever that's what we say may not be really realistic, but that's how we work right now. That's how it goes. So how could that eventually be that such a massive loss of kinetic energy happens when you look at the dimensions here?
Almost all the energy is converted to sound and thermal energy.
No, exactly. And probably it's when we think of the big ball, I mean, it's quite massively bigger, right? The mass is 4.5 times bigger than this one and comes at really higher speed, and that's an even square. So probably it really bangs into the small one. So that one might even be dented so that you have, which is not the case here, right? But in that situation, we would probably have to say the smaller ball gets some permanent damage, like maybe something gets chipped out. Maybe if it's a sphere, then maybe it gets a bit crashed in, so to speak, crushed in, so it's not perfectly round anymore, something like that. So all the energy we have, I mean, still, of course, very tiny, 3.8 joules, but in the relativity of the situation, it's massive. So that massive energy, if this sphere was of comparatively weak material, maybe, then of course it may have gone into deformation energy, right? But of course that would have to be stated. So with what you just said is correct. So there must have been some massive bang, really loud, and some significant heat, all in the relativity of the example, as an explanation of how it could happen. Because here we see clearly that that one got accelerated quite massively, which is kind of expected, right? Because the big ball obviously accelerates that smaller ball quite significantly. Under ideal conditions, there would have been no loss, so to speak. Also, let's go back where we have the proper before and after. So that even here it's still 0.86. So that means, of course, that speed here, that velocity would have to be much higher in order to still make it. And we can see in order to get that, it's probably, well, very similar velocity, so to speak. We could solve it now and say, this is now unknown, and say, okay, what would have to be the velocity after the impact in order to get a situation where there's an elastic collision. So no energy loss. Then you would have to solve it for a new whatever from the second ball y, so Vy2, so to speak. No? Then you would probably get something very similar in order to contain and keep the kinetic energy with no loss. No? So it's all in how the question is structured. So I see it's very thinking, Chris. And now we could go a bit into different material. So let's see what they ask. So we just jump ahead and see, okay, they say verify. So let's see if it's really elastic. So this time they don't tell us. So we have to prove it ourselves. And now we have an aluminium sphere into a steel sphere. But we'll see. Well, let's calculate it, and then we can eventually make some assumptions. So what is the situation you have to calculate?
10 times 2.7 plus 0 equals 2.7 V plus 5.1 times 7.9.
Okay. Yeah. Okay. Yep. Very nice. Okay. And so if we, of course, now we can just calculate it, rearrange it. It depends on what the teacher tells to see. So if it's a test, I mean a GCSE, excuse me, an A-level test, as a real test, a paper, then it's always good to write down before you. What I want to say is the following: you could now punch it out, right? Just calculate it, and then rearrange. It's usually better if you do a rearrangement and then calculate it. I'm not saying that you have to go back to this one, so to speak, and then rearrange the whole formula and then fill in the numbers. That no. But I would suggest that before calculating those individual parts, I would rather make a rearrangement in order to show a bit the situation. So, but I'm obviously, of course, 10 times 27, okay, that's a bit of borderline now. That is there. I would maybe say, well, that does not necessarily have to be written as 10 again. And what do we have to do in order to isolate the 2.7 V?
Um, 27 minus the 5.1.
Yeah, good one. Yep, that's important. That's why I would leave it like that. When again, times 10 is, yeah, no need to write it still as two individual factors. But this one is good because then you make a clear link to what was on the right-hand side, because for whatever reason, one never knows, you may punch it in the wrong way around. I mean, in terms, maybe suddenly we key in 6.9 or 7.8. Stuff happens, right? So it's, if you write it once more, it's crystal clear, and then it's 2.7 V. So what is my next step now in order to get V?
Just divide 2.7 on the other side.
Yeah, exactly. Yeah, exactly. Yeah. Straightforward. Exactly. So and then I would say it's time to punch it in, right? So and we would get, having done all that, minus 4.9 meters.
Wait, shouldn't it be 5.1 times 7.9?
Oh, yeah, thank you. Yep, see, okay. All right. And you can see already that is just from a rough calculation, this is 8 times 5, roughly. So that's about 40. So if I have 27 minus 40, I must be on the minus side. So that's a good cross check, right? Of whatever I divided with, it must be on the minus side, which will tell us then obviously something as well. And what will tell, so V, in which direction is V actually moving? I mean, aluminium after the collision?
Back, the left.
Backwards. Yep, exactly. Yeah. So actually not like this, but like this. So must be fully drawn. That's just a symbol, a representation. That doesn't mean that this one is direction, right? It's just a placeholder. Say, well, V, okay. As we don't know anything else at the time being, we of course placeholder we can draw it like that. No problem, but we should then be aware that if the result is minus, that we correct it afterwards in our drawing. So no, we actually talk about the V, which is going the other way. Okay, so now in elastic, now it becomes interesting. So old story, right? Collision is elastic. So what do we have to do, Chris, to determine if it's elastic, inelastic?
We calculate the kinetic energy of the before.
Yeah, exactly. And the after as well?
Yeah.
Okay, yep. Yeah. So we can make it like a 1 is before, and kinetic is after, and then we can make the question mark, right? Is it? Let's see. Or if it's elastic, we can as well replace it and say, but it says verify that it is elastic. So when it says verify, is it elastic? That usually means we say it's elastic, prove it. That would be another way to say it. Otherwise, it would not be said verify. It would be like check. If it says check if it's elastic, then you cannot be sure. That word implies that it may be elastic, it may be inelastic. But if it says verify that it's elastic, that really means in 99% of the cases, it's elastic, now prove it. And we have it here. Here it's the other way around. It's explain that it is inelastic, right? So that is another way to phrase it. Verify that it's elastic, explain that it is elastic, same thing. So the wording is always gives us a hint. And therefore, we could say as well, okay, according to that, this is verified, so that means I will prove that. Doesn't matter for my calculations, I still have to calculate before and after, and then I see the result. So in any case, I have to do that. What is now my kinetic energy before?
1/2 times 2.7 times 10 squared.
Okay. And after, or maybe for the sake of I make the plus 0, just to clearly identify that. Okay. And what about after?
1/2 times 2.7 times 4.9.
Yeah, or I make it maybe, yeah, and write minus. I know, of course, it will not change, but do write the minus nevertheless. Of course, for the square, it will not matter anymore. But for the sake of the consistency, that the values are the same, include the minus as well. If you don't do it, you probably will not get any deduction, but it's just neater. So to write it like that. Okay, then of course the 7.9. And what is the velocity?
5.1 squared.
Yep. Okay.
Wait,
All right.
shouldn't it be plus?
Yeah, plus L. Yep. Thank you. That was a mental. Yep. minus 2 minus. Okay, so if I calculate all that, I get before for 135 joules. Just go ahead. The other one, of course, is a bit more complicated. There's more risks of getting a wrong number, but lo and behold, in the end, it will be the same. So conclusion, they're identical. So this one, it's the same. I proved it. Yeah? So they're really the same. What my original proof that was has been proven that it is the same. No? Okay. Let me just see. That's a bit too similar. Just instead of having balls, we have blocks. I can send you that after the lesson, of course. I will send it to the center, the whole paper anyway. I think that one is now. Okay, that's a good one, yeah, because now we have something a bit different. With first of all, it's with asteroid, but again, as I say, in the end, we have to separate it a bit, but it makes it a bit sounding more realistic. So we have a fast-moving small asteroid hitting a slower-moving big asteroid. They kind of melt or embed. B impacts, obviously, then spread somehow on and into the A asteroid. And so the first one is 2 marks already. What is the principle of conservation? How would you phrase it?
The total momentum before collision remains is the same as total momentum after collision.
Yeah, that's good. Very good. What you could say here, that is a bit when you think of our pulley question. Remember when we had this one, and then we had the elevator. Then we had to say, well, this is the whole system, so we have to include both masses for the whole, or the forces in the end from the two masses, resulting from the two masses. We could as well say the system or the momentum of a system remains constant. That's another way. So if we look at the system, and say like this one, so the system remains constant, right? There's no change, so there's no delta involved of a conservation of linear momentum. Or we split it and say before equals to after, or we can say it remains constant, the momentum of the system. So that's a bit along the lines of what we saw there with the two masses for the buoy, that we think of both, so to speak. Okay, and how do I get the second mark? What kind of condition do I have to state in order to make it really correct?
Under no influence from external forces.
Yeah, very good. And that's where the system, that's why the first one, the momentum of a system remains constant, is quite helpful, because say, well, everything happens within the box, right?
Yeah.
So that must conserve itself, and there's nothing external. So that's why the system approach is kind of helpful to come up with that external one. A bit easier, let's say, because of course, obviously we can come up with the same idea when we look at before and after. But there's a bit of a temptation for some maybe sometimes to think of external, whereas if we draw the system line like that, crystal clear. Yes, there's no other force. The moment there's an external force, of course, there's a totally different situation. Huh? Okay, very good. And there comes the next one, number 2. When you see show that the mass, what does that tell you? What do you have to do when it says show that?
Write the equation.
Yeah, right. It means nothing else but make the calculation and calculate the mass. exactly. So yeah, that is in math quite often as well the case. Then that it says show that, and then like f of x is equal to f of x1, for example, whatever that f of x then means. Then, of course, you obviously then have to rearrange the f of x so that it will result and look like the f of x1. So same thing here, right? Just calculate it. That's the meaning of show that. Okay, so how do we calculate that now? And we look at this is so then very important here, right? As always, of course. That makes life quite easy, comparatively, by properly digesting the information.
M times 3.61 equals.
Yeah, exactly.
Oh wait.
Yeah, you're on the right track. What is it?
Because
when you would put it down very abstract, yeah, you said times 3.6. What is that? What is that n times 3.6?
Times 1,000 meters per second.
You don't know n, right? So, in other words, what do you calculate here, Chris? What is n? That 3.61 is the velocity, right?
Yeah, but
obviously.
It's not in the same because it's km per second.
Yeah, okay, sorry, yeah. That's one thing we have to take into. Okay, I miss times 10 to the power of 3. Yeah. So what is that now? Okay, got it. That's good. So what is that n times v? Well, in as a formula, as a principle?
Mass times velocity is momentum.
Exactly, right? So, and if we now look at and see, okay, I have my momentum. Make it a bit nicer. So I have momentum. And I have my velocity. So I have my m. And I have my p. And I want to know. Sorry, the other way around. What do I say? So v, and I don't have my m. Okay, so the moment you write it down, right, it becomes quite some of these questions become very straightforward, but actually simple in the end. So what do we have to calculate now as a result of that?
So the 2 times 10 to the power 17 divided by 3.61 times 10 to the power 3.
Oops, yep. 3.61, sorry. Let's see, as a MSP. Exactly. And that's how much? Divided by 3 is about 0.6 times 10 to the power of 14, probably. 6, I mean, excuse me.
5.54 times 10 to the power of 13.
Okay, yep. So we can, you see, right, we could have said as well 0.554 times 10 to the power of 14. So, but usually it's a bit better. So there's nothing, of course, right or wrong. It's just that is usually a bit better. I agree with you. So to speak. If you have something, then better have 5 point something instead of 0.5. Then of course times 14. And What is the unit of measurement?
Meters per second.
What
Meters
have you
per
just
kg.
calculated, Chris?
Wait, no.
kg, exactly.
Kg.
Yep. Yep. kg, right? Just simple, straightforward. We talk about the mass. Now we found it. Okay. That seems to be rather heavy, but okay. On the top of my head, I couldn't recall what the weight of the Earth is. Maybe I have it somewhere. Sun is huge anyway, that's for sure. Don't we have it? Mass. Earth. Okay, the moon, just to say, okay, that gives us an idea. The moon is 7.3 times 10 to the power of 22. So it's obviously still much smaller. So it's really an asteroid, right? It's not just another moon flying around. And you see the difference. The Earth is about nearly 6 times 10 to the power of 24. And the moon is 7.35 times 10 to the power of 22. So it seems no big. So just, of course, it's factor 100, obviously, if you look at it like that. Numbers here don't matter so much anymore, right? Of course, when you go to the sun, it becomes rather wild. That's to 10 to the power of 30. Right? That's the beauty of the powers, right? You can instantly see, from the Earth to the sun, that's factor 6, but 10 to the power of 6 factor. So that's like a million. So the sun is a million times heavier than the Earth. Or in other words, you can put a million Earths, so to speak, assuming it's the same density, into the sphere of the sun. It's always good to have an idea, right? So that's clearly an asteroid because 10 to the power of 13 compared to 10 to the power of 22, or even of the moon. So that makes it a fraction of the moon. So we really talk about, yes, they chose it right. We have shown that. Now, what about B? Because now they go together, right? So it's one of those examples where we have not two balls moving anymore or two bodies.
So it's so the momentum of B plus A equals momentum of BA.
Okay, let me write that down. So we say the momentum of A plus the momentum of B, right, is equal to
the combined momentum.
Yeah, exactly. So PAB, so to speak. Huh? Okay, exactly. And how do I express that now in detail? Give me still the not the values yet. It's just I put it a bit higher up. So
I think for the momentum of A, we can directly use the value they gave.
okay, yep. So I'll just make it green because we know it. Yep. Okay. And then
for B, we use the mass times the velocity.
Okay. And do we have them both? Yep. So we can make them green as well. Start over again. So we have MP times VB, or 1 before the collision. This, of course, is before the collision. Okay, and then what is PAB, the combined velocity, momentum?
It's the mass of A plus mass of B times the velocity of after.
Exactly. No? So the velocity AB2, so to speak. Also, of course, there's only one, so we don't necessarily need the two, so to speak. Huh? Okay. All right. So that's why, with the colors, it's always very helpful as well, because then you can see instantly, okay, I know everything. Of course, not in values yet, I have to punch it in, but what I want to know is this one. So obviously, it's in that regards, a simple one equation with one unknown. That's it. So I just have to rearrange it in that regards, right? By keeping to the basic principle. It's very good, Chris, this one. Then we extend it, then we can just solve it for. So how is the rearranged calculation, or how does the rearranged equation look like?
The left side divided by MA plus MB.
Right, exactly. Which is kind of interesting, but very obvious, of course. That we say, okay, basically what we do is we divide the sum of the two momentums with the sum of the masses. And we get the velocity after the collision, or the velocity of the two bodies together. Right? It's kind of very obvious, of course, it's in the equation already, but it makes kind of perfect sense that we say, well, this one actually is nothing else but the sum of the two individual momentums, whatever they are, and I divided by the sum of the two masses. And that will result in the velocity of the combined body afterwards. Kind of elegant. Very logic, of course, very clear, but on the other hand, very elegant. So obviously, whatever momentum I had before, it's then heavily determined of the two individual masses, of course, which go all into the individual momentums as well, of how they relate the sum. So tiny, big, whatever. That's not even relevant in that sense, because it's just in the end the sum of the two masses which counts, right? Which makes perfect sense. And that determines heavily the velocity which is coming out of it. Okay, so if we punch that all in, we get, I'll just write it down, 4.69 times 10 to the power of 3 meter per second. Or in other words, 4.7 kilometers per second. So that's pretty fast, actually. But of course, it puts it a bit into perspective. So what is the speed of sound, Chris? Do you remember that?
I think it's 3 times. Wait, no.
Yeah, it's about 3. It's okay. I mean, it depends on the pressure and the humidity and stuff like that. So it's always a bit varying. It's no fixed value. And the temperature, of course. But 3 is a good approximation for general purposes. 3 times what? And it's not finished. It can't be 3 meters per second, right? That would be a bit slow.
I think it's 300.
Yeah. Yes, very good. Yep, it's 300. But usually we think in that dimension, right? 300 times 300 meters per second. So if I put it now into this perspective to compare it, right? So you can see the difference, right? So 3 times 10 to the power of 2, 300 meters per second. So and I can compare now the two numbers. So, well, this one is roughly 50% higher. 3 to 4.6 is about plus 50%, so 1.5 times, plus a whole power. So in other words, it's like, oops, I wanted to have right times 1.5 times 10 to the power of 1. So, or in other words, it's 15 times faster than the speed of sound. That gives us a bit of an idea, at least. So 15, that's when you think of, do you remember this, what we can say as well, when it breaks the sound barrier, would you remember the name we use for that barrier? Or when you achieve that velocity, when you achieve 300 meters per second, it has another name. Especially for the planes.
Is it supersonic or?
Yeah, that's one way to say supersonic or suprasonic. Yep. What is sometimes you hear is that Mach, also MACH.
Oh yeah. Mach 1.
That one exactly. Mach 1 exactly. That's exactly this one. So obviously 15 times. So I eliminate the 10. So it's just times 15. So obviously this is then Mach 15. Yeah? So that gives us the easy recognition, right? Like we say G force, right? Once the gravitational force or field of the Earth is 9.8, instead of thinking like 18 and whatever, nearly 20 and blah, blah, you can just say 1G, 2G, 3G, 4G, right? Makes life much easier in terms of discussions, at least. Same thing here. To say Mach 15 is like, wow, okay, that's really fast. Have you eventually seen the movie Top Gun?
The second one I've seen.
The new one, yeah, the latest one. The Maverick.
Yeah.
Right. So he was flying with his plane or his rocket plane into basically nearly outer space, not quite, just still close to Earth, but not yet leaving. Do you recall what the Mach he achieved? Which Mach?
I think he said almost 10 or.
Yeah, exactly. Very good. Yeah, exactly. Right. It was, of course, it's a movie. We don't really know, but it was shaking and rattling, and obviously the engine had to really bring the power. So for that very impressive scene, that was why Mach 10, right? Along the lines of what you just said exactly. Now, if you think that this asteroid is the combined velocity is Mach 15, so okay, that's quite something, right? So we went to increase it. That's the point here, right? 3.61 compared to 4.69. Huh? So that really, that tiny little asteroid really gave a push to the whole system in the end, huh? By having the impact, and pushed it up from 3.6 to 4.7, so about 28% acceleration, so to speak. So that's, of course, usually not being asked, but it's good to see the relationships a bit. That's what physics should be about, not just the calculations. Okay. Now, let me see. Yeah, let's see. We can maybe do the principle of that question. And obviously now it makes it more complicated by introducing angles. Huh? And now the combined AB collides with a simple C or single C asteroid. And they are deflected now in the respective angles. So we obviously have this situation. We don't, size-wise, it's a bit like this. And it was stationary. I mean, that's, of course, we would have to say, relatively speaking, stationary. But we cannot to imagine a stationary asteroid in space. That's not happening. It can only be the relativity. So, but then it makes no sense, right? Do you know what I mean, Chris? Because if I cannot, an object in space is moving, and the only thing which it is comes back to Newton. It may travel at a constant velocity, which is the same as mine. So it looks for the observer like we are not moving, for example, or the other, either me am not moving or the other one is not moving because we keep the same distance. So relatively speaking, we don't move towards each other or we don't go away from each other. So we feel like we are stationary. But for such a question here, to have a stationary asteroid, that's really not possible. But sometimes better not think too far for certain questions, because otherwise we will. It's just to make it more attractive instead of one ball hits the other ball and then hits the other ball. So it sounds a bit better with asteroid. But of course, there's no such thing as a stationary asteroid. And if they would be, relatively speaking, stationary, then they will move both as a system at the same velocity, and then they never hit each other, right? So the whole question becomes useless. Just to say, huh? But that's how the question is, in order to make it not too complicated. And what do we have to do in order to calculate the mass of the asteroid?
Find the horizontal component first.
Okay.
So for asteroid C is 21.3 sine 10.
Okay.
Oh,
All right.
cosine.
That's fine. I know you go make a big step forward, which is fine. But okay, so let's say this is P5, P stage 2. Okay, it's fine. We will still have to look at P stage 1. Okay, P stage 2 is just without the values first, maybe just the general equation, so to speak.
So it's the velocity times cosine 10 degrees.
Okay, so it doesn't change exactly. That's the important thing. So we have to combine, right?
Oh yeah.
So that's important. And then, of course, but because it had an angle, so we have to introduce it. And which one would that be? I mean, you said it like cos. You said, Chris. You said cos, right? Cosine.
Yeah.
Exactly. So we can say, so I mean, now I make it really abstract. So I say the angle theta for AB. And what is it for the asteroid C?
Mass of C times velocity C cosine angle of C.
Genau. So it becomes already very transparent. Sometimes the big numbers hinder us a bit for the big pictures. And what about P1 before?
We know the momentum of AB.
Okay, yep. So we just have AB times VAB, huh? And 0, because C is stationary, right? So
yeah,
we can as well make it crystal clear. Introduce here this VAB. This is 0. Okay, so we have it, right? So that means, and what do we state? And we need to know the mass, show the mass. So, okay, so mass C, I make that in red. Let's check, do I have the velocity of C? Yep, I have it. This is here. Do I have the velocity of the combined AB afterwards? Yep. Okay, I have to introduce a 2 here, not to make any mistakes. and therefore I have the mass. So then I can just, that's always the check, right? To say, do I really have all the values? So in other words, this is my BC, this is my VAB2, this is my VAB1. I obviously have the mass of VAB. I do have the mass of this one as well. So no change to that. So all I need is, oh, sorry, now I misled myself. Of course, you don't have the mass. That's exactly the point. So this one. Huh? All right, so then we just rearrange it. So as P1 is P2, just jot that down as well. So the usual no change. That's always the same in that regards, and then it just becomes a bit more complicated. And out of that, in the end, I can calculate my MC. In order to do so, Chris, just quickly, when we say this one now is equal to this one, so how do I isolate now MC?
First we move the AB momentum to
this one, huh? Mm-hmm. Yep, to the other side, right? So we put it minus, so we have this minus that, and divide it then with the velocity and the respective angle, or the contribution of the velocity in the direction of the asteroid in the x direction, right? And with the angle is only 8 degrees, so that's still probably quite substantial, right? If it would be up here, that's a different story, but 8 degrees, there's not much loss. That's still maybe 0.88, 0.9. So most of the original velocity remains in the x direction. And here, so similar, of course. Okay, so just as the final result is 1.3031 times 10 to the power of 13. Huh? So, and we had mass AB 3, that was 5.5, and the other one. Okay, so all right. What I will do, Chris, I will send you the whole paper because there's question 4 with this one. With typical, when you have the balls on a thread and then they bang into each other, what happens then? So there's a whole set of questions coming out of that. And there's something wrong. I have to correct that because this here. Okay, so there's a lot of questions. You see what it will do, and then we can eventually continue with those. For you, Chris, would you like to still to continue with momentum next time, or a different topic?
Huh?
For next lesson, should we continue with the momentum or start another topic?
Because I don't know if there's like any other like type of momentum question.
Well, you see here, because that becomes a bit different because you have this with the string, the balls with the string. There's something a bit special about that. It's a bit like here when we have to consider the angle. It's the standard. And question 5 is with a gunshot. So there's some, and we can, of course, that was we can go into the hard questions. There you see the hard questions. Maybe we do some hard questions next time, if it's okay for you. We still do momentum. They become really, you can see that's that's question 1. This one with the pellet hitting the fire. Maybe question 2, the good one we can do next time from the hard ones. I think then we have it covered. So if you still do momentum next time, that's fine. But I think after that, we really have it covered from a whole range from medium, that was considered medium now, but still quite some challenge to my opinion. But as you have it under control, that's fine. We see how that goes with some final, more complicated ones. Huh? Otherwise, just have the center, and then I can prepare accordingly for something else. Huh? But the medium one, I will send you that paper we discussed today with these still open ones, so you can have a look at it.
Yeah.
All right. Okay. Then have a good one and see you next week. Huh?
Yeah, see you.
Thank you. Bye, Chris.
Oh my god, oh my god. Oh my god. No. Why is the internet so slow?